recording. I wasn't going to do the recording of code, but why not? And so all we got to do is got to find this value. And now we do -1 from this value if it's positive, and the reason why is because it starts from 0, right? But if it's negative, we do not. And so the value range is going to be n-1 to 2 to the power of n-1 minus 1, right? And again, the reason why this is 1 less than this is because this includes 0, where this includes like -1, right? So the total number of options is still the same. It's just that this starts at 0, so it's like 0 indexed rather than like 1 indexed, quotation marks. Does that answer your question, Darius? So the reason that you would know it goes to negative numbers would be if it went larger than the largest positive number. Now, technically, this is not defined in this. So C has what's called a standard, which specifies behavior, and C standard specifies that overflow for signed numbers is not defined. So it can do whatever it wants. It just typically overflows like this, right? For unsigned numbers, it will always overflow like you would expect. So it'd go from like 0 to 255, and if you add 1, it would go back to 0, right? So it kind of repeats. And in the same way, typically signed numbers also overflow in that same way. But again, it is kind of undefined. And we talked about that somewhat last week when we went to the... Where's my coot? Where did it go? Did it really... Did it really exit? Did I press the exit button? I don't think I did. Oh, I didn't. I had just moved Alt tabbed it. Okay, it's here. I was so confused. And so we talked about it last week when we looked at the so if I could get up IO. I know this will be a bit weird because we're gonna be doing it and then stopping, then starting. But I think it's just if we can explain as we go through it, it may just make it a bit nicer. So if we took up week 2, right? One thing that we talked about was this, and I talked briefly about this stuff being implementation defined and stuff like that. And it's pretty much the same for addition as well, right? If it's going to overflow, it's implementation defined. Okay, let's go to the next question. And I'll stop a bit less for this one, I think. Yeah, so this one is basically the same thing, but saying how do you fix it so it prints 60,000? So the idea is that we've now realized that it's not printing the right value, so now we want to fix it. And for those who don't know what who means, the U means unsigned. So this means print a half unsigned number or a 16-bit number that's unsigned. And some of these have multiple answers, right? Some of them have only one answer. So if you go, oh, I can actually see like 2 answers that are correct, then maybe they're both correct, right? So don't worry too much. And for those who joined late, who still want to join, I believe you can still join. I'll just drop in the codes required in the chat. So we can see that basically every answer was right, but the last one. And so the point of this was because of the last one. I wanted to kind of just show the reason why the last one doesn't work. Okay, so let's talk about what each one does. So this is the obvious one. This is the one that most people got, and it's the most correct one, right? So all we've done is we've basically just casted this number to unsigned, and this will work, right? This is will work exactly how we expect. Yeah, but like, I did build this question so most people would guess it wrong. I'm impressed that so many people got 13, or got blue. A is correct, and the reason why it's correct is kind of the same reason why this one's correct. Actually, this one is not actually correct. That's wrong. This should be HU. Oops. So if you got, there's one person who got yellow who got lucky, but I didn't mean for this to be HU. If this was HU, this would also be correct. And it's for the same reason as this, right? And so the reason here is that when I'm passing this short as to this printf function, right? It's effectively just going to pass the value, and then it's going to interpret what the actual type of this is based on this, because it's a variadic function. So at this point, we're basically just passing binary bits that we're reinterpreting. So when we reinterpret it as an unsigned number, it will just work, right? and so it will be fine, and we'll get 6,000. But when we, for example, do this one here, we would go HD, and then we do unsigned short. This will again work if it's you, because if it's you, it's just, again, we're just doing this extra cast here for no real reason. But this is going to do the same thing. Again, this cast is a little undefined because it is going to cause when you do the cast, it's going to cause it to overflow, or rather, it's a negative number, so it's going to cause it to underflow. But it's still reasonably well defined on most systems. It just could be different. And I can show you how it works if I bring this over. And I don't. There's this one that also has the last answer. The cast isn't important in this case, but it's typically important, which is why I included it. The reason why it's not important in this case is due to the fact that this is variadic. So this basically doesn't have a type for these arguments, and so interprets the type based upon the parameters you give it here, based upon the format. So the cast is not important because it implicitly does a cast. But like, for example, if you wanted to do like, I don't know, let's say you wanted to do where you do MIPS and stuff, and you want to do things like register location moving and stuff like that. If you're trying to like emulate MIPS, it does become important what type everything has. And this is one of the reasons I did this question. We'll come back to this a bit later when we talk about how to swap between interpretations and narrowing and stuff. Anyway, and so one of the things that we see here is that, and if we run it, oh, it's just adjuvant cause undefined payer. So this one's also going to be wrong for the same undefined reason, because it's going to overflow. Anyway, we'll talk about that in a second. So what we have here is we have this one here, which is the int, which is obviously wrong. It's just going to cause it to underflow to its overflow to its overflowed value, and then it's just reinterpreting that as a negative value. This one here is right, as we can see, because it's just going to literally sum these numbers up. It's fine. The reason why this one here is wrong is because this is char, not short. I think I said short here. Yeah, I just can't retype it out. So if I make it a short again, it should be fine. Yeah, okay, good. I was a bit worried there for a second, but it's just, I can't copy things. So if we make it the same as this, again, ignoring the HD, if we make this HD, then, I mean, of course, this is not going to print, it will just print our negative number as we got back up here, right? Because again, this is the exact same thing that, this is, for the reason that this doesn't work, it's the same reason that this does work, right? Even though this is an unsigned short, we're asking for this to be a signed value, so it's going to interpret these binary bits based upon this format here, right? But regardless, if we make this what it's meant to be, which is you, we get the correct value. Awesome. Anyway, so most people got this one right. I think if you got red or yellow, there's probably like a 50% chance you're guessing, but still, because those ones are kind of the hidden behavior. Juice is winning. 420 in binary. I don't know. And you may want to just like, there's a few tricks for this one. Like you'll notice that the answers are quite different. And this is explicitly made. So I want you to be able to like look at a bunch of answers and be able to tell which one's correct without actually having to calculate it in your head, right? I wonder if this is a CSS animation or just a GIF or something. And bang, awesome. Okay, that's really good. So this one's really close too. So like, I'm sure this was a toss up, maybe. But the way you should be thinking about this is you should think about like, what's the largest multiple of 2 that you know, right? And so the largest multiple of 2 that I know that will fit into this is 256, right? Again, if you're not very good at calculating them, it's not that hard to begin from the bottom and calculate up. This won't compile. It's not a valid value. It's just, this is mainly just meant to like see whether or not enough, if like, let's say like the entire class selected OB420, I know I did something very wrong in the first shoot and would have to revisit binary numbers, right? A few people means that maybe like if you guess 420, maybe you just like misinterpreted it or something. Maybe you thought it was like a C extension, but like if there's enough people, it means something else. Um, that's cool. So in this case here, when we're choosing this value, right, we're looking at patterns that we know. And so the pattern here that I can look at is that this one's going to be 128, 256 rather, right? And so I know that since that's 256, that must fit in this number and it must include this bit, right? It's not going to include like 512. And again, just count up like 1, 2, 4, 8, 16, 32, 64, 128, 256, right? Um, you probably should try to do at least enough math that you can like count up to 1,000, like 1,024, without like any worries. Uh, any more than that is extreme. I mean, other than that, you could also just like look at like the position and be like, okay, this number is going to be very, very large, and this number is could potentially be good, close enough, but like this is at least you would toss it down to these two, right? Which is really what I wanted most people to be able to do. So that's good. Everyone seems like they know it. If you guess this one, it's okay, like because you probably looked at it and like this number's pretty close, and so is this number. Okay, it must be one of these two. Oh no! The drop. And then I give you the value in binary and I ask for you to convert hex. And answer, that's a beautiful tip. That's probably one of the best tips. And that tip is very useful. That's the reason why modulus and stuff works, right? You can basically write a modulus using a bitwise AND. If the number you're modding by is a multiple of 2. We will go for that in a second. And for the same reason that OB420 didn't work, this one also will not give you the right answer. Yay. Okay, that's really good. Right. Now again, this was probably a toss-up between these two because these two were the only values that were at all related to this. So this question was probably a bit easy. Like obviously you could probably see the 1 here, hopefully. And the 4 here was really the easiest way of doing it. You didn't even have to define what this value was. But you could. Okay. This is a bit easier than I thought. Or maybe everyone's just really good. So in a 32-bit float number, how large is the mantissa? Now I'm old apparently because I call it the mantissa. Apparently all the cool kids nowadays call it fraction, which just sounds, I don't know, like floats are pretty hard. Like why don't we just call them cool things, right? Make that sound like we're smarter. See, I'll always call it the mantissa. I try to call it fraction sometimes, but like it's just a gut reflex. But it's the same thing as the fraction part. This one's also probably most people will get. So there's two correct answers here. Now, the reason why I say there's two correct answers is because the question wasn't very specific. And so I wanted to talk about it. So I was like, the only way I can really talk about this is if I give them both are correct. So this, no, not unsigned versus signed, but the kind of an interesting idea. Yeah, I guess you could say that, but no. If you had like an unsigned float, you could use the extra bit in the mantissa. Um, so this is 100%, right? So this is the actual like how large it is on the system. And Josh is 100% correct by saying it's 24 bits because there's an invisible bit at the front, which represents 1 for your normal numbers. If you have a subnormal number, then that invisible bit goes away. And we'll talk about what the invisible bit is in a few moments, but right now we can just say there's an invisible bit at the front for normal numbers. And we only ever deal with normal numbers in this course. You never have to deal with subnormal. I'll briefly explain what subnormal numbers are, but we won't really deal with them. Okay. No, the invisible bit basically represents the fraction 2 to the power of 0, which is 1. So it's basically just like a +1 to your mantissa. That always happens if your number is normal. So like, do you know how your mantissa could be like a half plus a quarter plus a third plus this eighth and so on? It just adds like an extra +1. We'll go for it in a second. Yeah, don't worry about it if you don't understand that. So those people who said blue, I hopefully didn't just guess. Hopefully you knew that. I mean, I doubt it, but maybe. I wouldn't have known that. I would just guess 23. Okay. What purpose does a bias serve in an exponent? Does it give you a signed exponent, or is it actually just 2's complement? And we're just saying a bias just is an easy way to calculate it. And by to give you a signed exponent, I mean like it's not just 2's complement. There's like a specific reason why it exists. Because 2's complement doesn't actually have a bias. Awesome. So let me just explain this. So the reason why it's not actually 2's complement is because there's a few reasons why. We could make it 2's complement, right? But the reason why we don't make it 2's complement is because it actually makes comparisons between numbers much harder, right? So a common thing we want to do is we want to be able to compare floats to other floats, and we want to be able to compare them in a way that makes just like the actual whole system easier. And so we can't just take a bias of we can't just take a 2's complement of the entire exponent, because it makes that comparison harder, right? Because you effectively, you end up with cases where it's harder to compare how big an exponent is to another exponent, because all signed values become larger than all unsigned values, if that makes sense, right? Because obviously signed values begin at -128, and if we compare this as like an unsigned value, if we don't actually interpret this in any way and we just compare it as like raw data, these values are always going to be larger than these, right? And with the exponent, it's the opposite way around. So because we're subtracting 127 every single time, right? The smallest possible value is going to be 0 and the largest possible value is going to be 255. So the order that the values go in is the same. So for our bias, the smallest possible value is this, right? And then the largest possible value is this. See how it's like the opposite way around? It just makes life easier. Now, technically, with most wait, I did that wrong. 128. Technically, with most floats, it's really just 1 to 127, because 128 is infinity, right? It's got like a special value, as we'll go through later. But I guess we can still count it. Ooh. Some people have gotten most questions correct, which is pretty nice. This is kind of talking about what we said before. We already talked about like how you can tell whether or not a number is negative. Obviously, you need to know the bit size of it. If you don't know the bit size of it, it's much harder, but not impossible. And the way you can do that is using that trick I talked about last time, where what you do is what you do is you can do this trick to basically find where the very leftmost bit will be in the number, and you can use like a negation of flip and so on. So like if I do, we look at these things here. One of the ones here is this. So this right moving mask, this will find the very leftmost bit, and so you can check whether or not that bit is set, right? And I mean, obviously you can just say less than 0, right? That's a much away, right? But like if you wanted to like do it purely using bitwise arithmetic and didn't want to compare. And so again, for those people who missed it before, right? If the very first bit is set, it has to be negative because otherwise it's going to be too large, right? Because we're splitting the values in half, and so half the values go to one side, the other half go to the other side, right? And so the values get split in half, then we're just dividing the number of options by 2, and so we're basically dividing 2 to the power of 8 by 2, which gives us 2 to the power of 7. Basically means there's 7 bits associated with the value. Okay. Then the last question before we actually maybe write some code, which is what does this produce? So it's just a kind of a recap from last week. You may want to write them down, maybe if that makes it easier, like type them down so you can like view them like vertically. I didn't make it that hard. I kind of made the way they line up a little bit easy to see, just because I knew it would be harder if you can't view it vertically. Ooh, this one's actually getting a few people. Yay. People rush towards the end. So yeah. So it was a toss up between probably 2 of the values, right? And so again, when you're doing questions like this, you can break it into pieces, or you can just like recognize patterns, right? So the first thing that we recognize is that this pattern here is going to remove this bit, but then it's going to get reset by this XOR, because XOR toggles a bit, right? So it's going to turn it on if it's off, and if it's already on, it's going to turn it off. So, this result here is going to be off for the first bit, so it's going to turn the first bit back on. We can ignore most of these, obviously, and then for these, we only have to include the first 2 bits here, because the other 2 are going to be off, because, zeros. And so then with these bits, we're just finding which bit matches it, and this bit matches this bit. And again, it's XOR, so it's going to turn it off. So blue and green were basically the same thing, and it's basically just testing whether you know XOR, right? So XOR toggles bits, turns it off if it's on, and turns it on if it's off. The other way you can think of it is if they're both on, it goes off. If one of them is on, it goes on, right? And that's it. So we can see who won. See if it's a pronounceable name or just like an icon. Name. Okay, wow. Okay. Good job, name. You won. And last place, Emin also got pretty close, which is good. Number 6. Good job. And so we can find that this was the really hard question that most people got, but like I can you can look through these and see. But effectively, 59% of people, or 59% of people got. I don't know what this means. Does this just mean 59% of all answers were correct? Which is actually pretty good, because as I said before, I was looking for like an average of around 60 to 70%. So I'm happy with that. Obviously, there's some people who got less right, but I think on average, most people got most of them correct, which is very, very good. Again, that'll probably be a bit easier than expected, but that's still good. Okay. So let's go into week 3. So we already did most of these questions like this. So again, just to recap, this is going to produce a negative number because this is going to overflow. And we can just make this int to do a positive number, or we can also change the size of this to u or something like that, right? Two's complement. So if we're going to convert something to two's complement, what we're basically asking here is we want to convert back to decimal, right? And so this is something that maybe some people don't know how to do. So let's look at this. The first thing we should always do is find out how big the value is. Now, it doesn't say how big the value is here, but they all have the same size. And this is 0, 0 at the front, right? So if it has 0, 0 at the front, you can presume this is the actual integer size, which is 4 bits. Oh, sorry, 4 groups of 4 bits, which would make it 16 bits total. So if we just like expand these, we get like this. Again, 1, 2, 3, 4. And then to convert this to decimal, right, all we have to recognize is this negative, right? If it isn't negative, we just read it back out as decimal. If it is negative, then we have to, flip the bits or subtract 1 first, then flip the bits, right? Because obviously to convert it to 2's complement, you flip bits and add 1. So if you want to convert back, you subtract 1 and then flip the bits. So I guess you go like result -1 and then flipped. Okay. If we look at it like this. So you can do some simple math to realize how that comes about. Okay, and so in this case, this is going to be positive because we can recognize it immediately. And so we can just map this out and we can look at the exact value, we can sum them up. It's going to be 4 plus 16 plus 32 and so on, right? I could sum those up, but I just won't. I'll just look at the result here. And the answer is going to be, oh, that's fun. It just still keeps as this. I don't know. This tool is okay. It's just sometimes it's hard to know exactly what I want at any one period in time. Anyway, and so one of the things it does here is this is going to convert the value to 4660. I just chuck in Python. Python's like a really quick way of doing it. Most of the arithmetic I do ever is in Python. For things like this, you can just say hex, you can say OB. If you want a binary number, you can say OX. Like it just works, and you don't have to know Python. You can just like type it in. It's just a super easy way of doing it. Okay. So here we have it. And now what you could do is just figure out, for example, FFF, right? This one will be a very different value, right? And so if we want to convert FFF, that's just going to become this, because F is 15 in every position. Now, obviously, we know this is the largest possible value. And I talked about before what the largest possible value was. It's going to be -1, but we can verify that, right? And so if we subtract 1, what happens? Well, if we subtract 1, we get this. And then if we flip it, we get everything being zeros, but 1. And then we reinterpret it. I guess you chuck a negative sign out the front just to make that simple. And then we reinterpret it as -1. Does that make sense? So if it's negative, and you can tell it's negative by, again, the first bit, you're going to subtract 1, flip it, and then reinterpret it as negative. And you can see the values here like OX8000. Which, you subtract 1, you can get 1 in all these positions, and then you flip it. How did I do this flip? To this. This is just subtraction. So I just did subtract this. So this isn't the flip, this is the subtract 1. And then once you have this value here, you do the flip next. And then for the OX1000, let's just do this one because this one's, I think, it kind of cleans everything up quite nicely. And this is the case I was talking about before, about the weirdness around if you get to the maximum value. If we flip this value, because obviously it's going to be negative, first we subtract 1. Right? This is going to produce a unique value where basically everything is 1 but the first digit. Right? Because obviously if we subtract 1, this is going to toggle, and then to make this toggle off, we need to like borrow bits, and we borrow bits from all the way to the right. Then all we go do is just flip it. So if we flip this, we end up with the same number we started with. Again, it's the negative version of the same number we started with, which makes it -128. Which is one of the reasons why if you do -128 in C, you get -128. These don't cancel. It's also kind of the bane of most C programmers' existence once you actually start doing some certain there's some certain stuff around like certain algorithms and stuff that break quite ugly when you have this certain value here because of things like this, right? So for example, a negation function does not work. So like this function here has technically undefined behavior because of this one case. So there's always trade-offs. Keep going. So in reverse, I'm probably not going to do this. I'll do like 5, but because it's pretty simple. If you want something like this that's positive, you don't do anything. Just literally just convert it as is to binary. That's all you got to do. It's only if it's negative that you have to do something. So if we want to convert -5, let's say we convert to 8 bits, just to make our lives easier. We convert first 5 to binary, which is just going to be this. And that's 5. And all we got to do is just flip the bits and add 1. So we flip the bits, add 1. So this is flipped. Then we add. Right? And that's the interpretation for 5. And again, we can kind of see why. Our weekly test should be this week, probably Thursday. It may be next week though, but it should be this week, Thursday. And the other thing that we can realize about this is if we add, we subtract 1 again, we're kind of, as I said before, instead of going left to right, instead of going right to left, it's going to go left to right. So if we subtract 1, we're effectively going to end up with the next number in the sequence, right? Then if we do again, and so on, you're going to end up with something like this. Like, see how it's kind of growing. Actually, you're going to end up with something like this, I think. And then finally, eventually, I don't know. It's going to go some way like that. I can't do that. -1 in my head is a bit weird. Like to convert -1, you'd have to convert to binary, which means like flip the bits and add 1. So you would end up with 1s in every position. I think that's just going to lead to like when you add them together, you get like weird cases because like obviously the 1s are going to add in certain bits of places like this and so on. Anyway, but yeah, you're going to end up with some values because the 1s are going to add here, then propagate, and then flip things, and it's going to be weird. Anyway. What decimal numbers do the following single precision IE 754 bits represent? Okay. Let's do a few. The rest of the stuff is also important. So okay, so we'll do a few. So floating point numbers is one of those things that you guys kind of have to do yourself, I guess. There's so many ways you can do it. I will do a few and show you how to do them, but like I do recommend sitting down and doing a few of them yourselves. Because they're not easy to do if you haven't done them before. And they get pretty easy, but they are still at the beginning a bit tricky, especially in reverse. Reverse is annoying. All right, let's just begin. So we're going to begin with one that looks okay, like this one, sure. I don't really. So to convert this number to yeah, a decimal value, I guess. All you got to do is you just got to recognize the sign bit first. So this is the sign bit here. So it's obviously going to be positive because it's flipped, or because it's not flipped. So it's going to be positive. And then the next thing that we have, I mean, we can see it here, right? For example, the second bit here, this bit's 1, right? And it's going to be negative, or it's going to be -0, I guess, because these values have the same representation, right? Anyway, it's kind of weird how they've got -0 there, but nothing else is negative. Anyway, so the rest of this is we just going to convert this bit to, you know, binary or decimal rather, and find out the exponent. So this is going to be 8 bits, which means the maximum value is going to be 256, right? Or rather 255 if we're doing it. Wait, no, it will be 25. No, it's gonna be 128. I can't do it. Yeah, it's gonna be 128 because it will be 1, 2, 4, 8, 16, 32, 64, 128. And then we got 128 here, and then we're going to subtract 127 from it. This is our bias, right? And that's going to give us 1. So basically, this is saying it's 2 to the power 1. Okay. And then all we got to do here is we just got to sum up these values. And because it's normal, therefore plus 1, right? To Manchester, just always pretend it's normal. Subnormal numbers are annoying, and we may talk about them in a second, but they're not really relevant for the course. And so in this case, this is going to be plus 1, or rather 1 plus, I guess. And then this is a half, this would be a quarter, an eighth, and so on. So rather it's 0 times 2 to the power of -1 plus 1 times 2 to the power of -2 plus 1 times 2 to the power of -3 plus 0 times -4 and so on, right? So when you do these kind of questions, basically you think of these as like flags that are set on and off. And so if we sum up these values, we get 1 plus 0.5 times 0, I guess, plus 0 plus 1 times 0.25 plus 1 times 0.125, and then the rest is 0, thank goodness. And so again, this is a half, a quarter, an eighth. And so if we sum these up, we should get 1 plus 0.25 plus 0.125, which is equal to 1.375. And we can check the answer here. Times 2, which is equal to 5. Which is the answer here. Right? And just to kind of recap what I did there, is I found the Mantissa values 1.375, and then all I did was times it by the biased exponent. And I almost had a heart attack because I was like, that's 1.375 is not the answer here. Oh man, it's stressful. Anyway, now we're going to do one other value, which is 0. Now, almost quite a few people get 0 wrong. And the reason they get it wrong is what they do is they do something like this. This is why you kind of have to care in some small way about, can I just copy this? I can. I did that right. This is why you kind of have to care about for subnormal numbers, because they actually do matter in this very specific case. So if we look at this value here, the first interpretation is you go, okay, this is positive because of the 0. The psi Mantissa is 0 minus 127. Okay, therefore it's negative 127. And then this is going to be 1. This is the first interpretation that people say. They go, oh, it's normal. Right? Therefore plus 1. So therefore they say it's going to be 1 times 2 to the power of negative 127, which is approximately 0. Right? That's wrong. The actual answer to this is exactly 0. And the reason why is to do with the fact of subnormal numbers. And subnormal numbers are a specific class of floating point numbers. And basically, they do not have the extra plus 1. Or a subnormal number is, I think if you Google it, it will probably call it denormal, but they're now, if you look at like the Wikipedia, it says, I'm looking at it now, it says in computer science, denormal numbers, now often called subnormal numbers. The reason why is because there's actually some clarification around denormal. It can mean other things as well in other contexts. So subnormal is technically better. And effectively, all it is used for is just to give you extra precision values between 0 and 1, and that's it. And so the way it's typically interpreted is that subnormal numbers are encoded with a biased exponent of 0 and whatever this is. Now that's a very simple way of doing it. There's other ways you can do it too, right? But the simplest way of doing it is you basically just say, hey, if the exponent is 0, right, then therefore we're not going to add the 0. So what actually happens here is it goes 0 minus 127. This still occurs, but it's subnormal because exponent equals 0. Therefore, plus 0, I guess, right? And so therefore it becomes 0 times 2 to the power of 1 negative 127. It's obviously going to be 0. Okay. And that's it. That's all you got to know. There's not much else to it. Now, technically, even this is incorrect because in a subnormal number, the exponent is actually negative 126, not negative 127. And I do know that's confusing. That's just how it works because it's subnormal. And you don't have to worry about subnormal numbers in this course at whatsoever, but that is kind of how they work there. If you have any questions about that, feel free to ask. Else we'll just move on. So that's basically the way you solve these things is you just like pretend they're normal, right? And all you're going to do is you're just going to look for each value and you're just going to like find what the exponent is, minus 127, count up all the on bits in the mantissa, equate them to the fractional parts, and then just add them up. So in reverse, let's say we want to find what 27 is, right? All we're going to do is try to find like, well, I guess there's a few ways you can do this, right? There's a few ways you can approach this. The first thing is the sign bit. So we know the sign bit's 0, right? Now, the next thing that we need to approach this with is we need some way to solve it, right? Such that we can get a mantissa and an exponent from it. And there's so many different ways of doing this. I'm sure there'll be some different ways that people want to do it. But the way I typically do it is I look at like the pattern in the number, right? Because it's obviously got to be a multiple of 2. And then that multiple of 2 has to be composed of fractions of 2, right? So I typically look and go, okay, if I go 27 divided by 2, just to begin with, right? What do I get, right? And the result answer is that the fraction here, right, has to sum up to 1. Or like that's the, I mean, it can't technically ever reach 1, but like that's theoretically like the largest value can be, right? Because you've got a half plus a quarter plus plus an eighth, right? And all these will sum up and they'll never reach that. It's always gonna be like 0.9999 or whatever, right? As like the maximum value. And so what we want to do is we want to try to find a multiple of 2 that reaches this value below 1. So 0 obviously divided by 2 is not going to work, right? That's just going to give us like what? It's going to be like 10, 13.5, I think. I don't know. For some reason that's hard for my brain. Yeah, okay. Divide by 4, no. Divide by 8, no. Divide by 16, no. Divide by 32, yes. We're going to stop here at 32. Right? And then all we have to do now is just find a sum of the mantissa flags that equate to this. So if our exponent is 32, the first thing we want to do is we want to 32 plus, and it's not really 32, is it? It's like 32, it's like the log 2 of 32, if that makes sense. Or in reality, it's going to be 2 to the power of 5. So let's mark it as such. So it's going to be 2 to the power of 5, and therefore our exponent is going to be 5 plus 127, which is going to be 132. And then we're going to grab this value here and we're going to find the mantissa, right? So the mantissa, or fraction, whatever you want to call it, is going to equal, I mean, it has to be at least a half, right? Probably. And we're going to solve it the exact same way that we solve most of our problems with binary values. Is what we're going to do is we're just going to try like find the largest possible value that will fit in this, include it, then subtract it. So we're going to do 0.484375 minus 0.5, and that gives us 0.34375. And then we keep going. I add 0.25. And there's another way to that people like, which is like you basically convert it to like a decimal value. You can just like read off the flags from the decimal value. That will also work as well. It's up to you whether you want to convert to binary or not. I just kind of prefer this because this the way is quite quick, if that makes sense. So this becomes 1, and then obviously I'm going to subtract 4 from here, which requires a bit from here, right? And so I can quickly do it like this. So 5, and we get this value, right? And so on, right? And you can do this in your head if you care. I'm not going to do it in my head just because I don't want to make a mistake. And then the next one's really easy. Right? 1, 2, 5 can't fit, and so on, right? And so all you're going to do is just going to repeat this for every value until you reach approximately 0, right? But this is like a little slow. And so the other way you can do it that makes it really nice is what you can do is you can basically just kind of like move it across, right? And so all you're going to be looking at is if you want to convert a 0.25 is you can just kind of I don't know, there's a few ways you can do it, I guess. But I think the nicest way I've seen is you try to keep like a 0 here, and then you can kind of convert this value here to binary, and that will read out typically. So if we convert this value here to binary, then we'll get it. Anyway, so we could do that if we wanted. Grab my Python here. Let it, and then just grab the binary value and bring it across. We can do that. Anyway, okay, so I mean, I don't know how much if I want to go into this because converting this one to binary kind of sucks. It just takes a while. Maybe we'll do like an easy one, just because otherwise it's gonna just it just like takes a while to do it one by one. I don't know. I just kind of prefer it this way. Anyway, so you can subtract this, so then you can keep going, and you could subtract 0.0. But that is like I don't know. Again, for some reason I can't do that in my head. It's like a sleep. 0.625. And if you subtract 0.0625, the 9 and the 6 are going to go away. So you're going to end up with 3, then the 1, then the 2, then the 5, and so on. But then you're just going to keep going. And for each bit, you can just set the correct bit that's toggled. Okay. Are there any questions about that? The other way you can do it, that I do see people saying, is I don't know. I guess every year. I don't know. I don't like it, and I feel like it's complicated, but why not? We'll show off. And I feel like this is maybe what they teach in lectures. I don't know. Tell me if it is. All you got to do is basically convert the number 2.625, or like, for example, or in this case, it would be, I just got my notes 0.2.625. In this case, it would be what? This 27, sure. And we're just going to grab 27, and we're just going to convert them equally to the integral part and the non-integral part. And then we're just going to like combine them together to form the fractional and non-fractional. So we're going to divide this by 2 over and over again to get this, right? And then all we got to do is we basically just going to generate a bunch of the subsequent numbers. And so, for example, we're just going to times it. I think it's some people go like they times it by 2 over and again. I don't know. I just hate it because I feel like the way you do it is like you're just going to kind of read the binary from this, but you have to like move it around and shift it to the right position. I don't really want to spend time about it. Maybe I'll release like a slide that shows you how to do that in the slow way. But I feel like it's just if you just subtract it for this course because it's online anyway, you don't really need it. And it's just kind of a waste of like brain space. And it's just kind of weird, and it's a consequence of the system, which isn't necessarily always good. Anyway, so let's say we want to extract the middle 6 bits of this. It's pretty easy. All we want to do here is we just want to try to find a bit pattern that matches these middle 6 bits. And so what we have to do is, there's a few ways you could do it, I guess. You could try to like shift a position into place, or you could just try to like choose the position. So if you want to choose the position, you get like OX 0, 0, 0 for these 3 bits. And then this one here would be 7. Here would also be, or it wouldn't be 7, but it'd be the kind of opposite way around. It'd be 8 plus 12, 14. So it'd be E, and then it'd be 0, 0, 0. Now, if you want to go the opposite way around, where you basically just move up into position, all it's going to be is just 7E shifted by how much? Well, okay, you go shift this bit by 4, 8, 16, I can't do math. 4, 8, 12, 16. And so therefore all the other bits will be the same. Right? So for example, the bit that comes from here, well, it's actually not going to be that. It's going to be 4, 8, 12, isn't it? And obviously the reason there is that you want to shift this bit into this bit here and this bit into this bit here, right? So you're trying to shift this sequence of numbers from these sequence of numbers. And so all you're going to be doing is trying to find the matching pairs and just trying to find the difference between them. And so it's just going to be, there's 4 bits here to shift by, there's 8 bits here to shift by, and then finally that's 12. Okay. So these are the 2 ways you could do it. You could also just, I guess, count how many there are here. There's 3 pairs of 4, so that's going to be 12. Sure. And then we're just going to talk about unions briefly, then we'll stop. So the difference between the following 2 things here is all we're looking at is we're trying to find out location of the stuff. So for example, with a struct, they're located right after each other, right? So they're what we call I guess you can think of them as a structure is like a grouping that groups A and B together. So it puts them side by side. And so the size of this structure is going to be 4 bytes plus 4 bytes, right? Because a float is 4 bytes. It's a float 32. So the total size will be 8 bytes. A union, rather, instead of sticking them together, it sticks them on top of each other. So they both start at the exact same address. And more importantly, it means that the size of the struct is defined by the size of the union is defined by the largest member. So in this case, since they've got the same size, the size of the union is just going to be 4. It's just going to be 4 bytes because they're on top of each other. So what that means is if I modify A, B will also modify to be the binary equivalent of that value. So what I mean by that is if we have something like this and we go language is C, and we go void main void, and we make it int because I'm not crazy, and return 0. If we create our union here called x, let's create it locally because it doesn't actually matter where we create it. And we go x2.a, and the reason why this works is because this is where you put the type of the union, right? This with like type name. Put it here, it's just going to create a temporary union that puts x2. So it's not actually going to be able to create anywhere else, right? So I can't create like another copy of it. Like if I want to create another copy, I can type the whole thing out again. Right. So x2a, I can set this to 0, and then if I read b, the value of b will also just be 0 in every position, which will also be 0, luckily enough, right? But if I go x2 to a equals 8, right? The value of b will be, if we look at the binary equivalent, again, this is 30 bits, so there's going to be a lot of zeros, but eventually it's just going to be 1, 0, 0, 0, 0, right? Because this is 8 in binary. And the floating point value of this is not going to be, right, the floating point value here, right? It's not going to be 8. This is not going to be 8.0. We can find what the floating point value of this is. I mean, it's going to be subnormal, but okay. We already know how to solve subnormal numbers. It's just the exponent is minus 126, and it's 0 plus. So it's going to be 2 to the power of negative 126 times by, well, that's going to be annoying. I'm going to count all the way to the right. But it's going to be 2 to the power of, we talked about the mantissa being 23 bits. So if it's 23 bits, it means the very last one's going to be 22. And then that's going to be, this is going to be 22. This is going to be 21, 20, 19. It's going to be 2 to the power of negative 19. So I think it's going to be this. Right? And we can see that if we actually just hijack one of these and change the light theme to something a bit more readable, and then if we just chuck in OFB, or no, I think it's just FB, isn't it? Yeah, it's just FB. Awesome. FB, and then we just say 100. We can find this is our 32-bit float, and this is what the value is. And if we reinterpret what this is, and we ask, very kindly, I guess it's gonna be that, right? Cool. of -19, which equals this. And so if we chuck this in, we'll get this, which is pretty awfully close to this. I may have missed one. I may have done, yeah, so it should have been 2 to the power of -20 again. So I can't count. It's going to be, well, you can't see how I can do it there, right? Easy. So obviously that's not going to be 8.0. And we can look at the locations here. So this is located at 1000 and this is located at 2000 or OX 2000, right? And OX 1000. The values of A in this case would be, OX 1000, OX 1000. B here will start at OX 1004, and this would be OX 1000, right? Because again, the address does not change because these are placed on top of each other. Again, the union size is the size of the member, right? So this is going to be 4 bytes. This is going to be 1 byte. This is going to be 12 bytes, 14 bytes. Now there will be padding, which will make it slightly different. So most likely it'll be padded to like a multiple of 4, so 16 bytes, right? But yeah. Then down here we'll have this here, which is going to be 8 bytes because this element here is 2 pairs of integers. And we can see the insurance here. And then finally, when we print our union, what will happen again is that because all the binary value changes for all of them at once, if we change the integer to like say like 10, then it will also change the character to 10, and this character to 10, and this character, this floating point to the binary value of 10. And this value will also be the binary value of 10. If we change to unsigned int. Unsigned integer doesn't change the size. An unsigned int has the same size as this normal int. Like the number of bits is the same size. You are correct in saying there's more values that can be represented, but that's because there aren't any negative values. So they're like the bits that you have to play with is doubled because you don't have to deal with negative. Oh, if we change A here, then the X will change. Because the X will be located at the same address, right? The Y will be located at address +4 because this is a struct. So the struct here starts at the same address as everything else here, right? But the struct itself is not a union. Yeah, so A, B, and X will have the same address. And so for the same reason, A here will have the same address as the first 4 characters of this array. I mean, I shouldn't say the first 4 characters, or rather, the A will have the same address as the first character of this array here, right? And then the other characters obviously will be +1 to that address, right? But A will represent the first 4. Awesome. Is there anything else? I think this is basically everything. Let's see. And also someone just sent me this, which would be a useful thing. So if you want to find out the other way of doing it, this site goes for it pretty well. Right, I'll pull up on this here. And I don't have time now to go through it, but we can have a look at it. And it's basically another way of doing it. So rather than having to calculate by hand each time, and this is probably where I got my 2.625 from. All you're trying to do is you're basically going to convert the 2 to like binary, which is what this is representing, right? And the _2 is just this is binary, this is base 10. So I'm converting my 2 here to binary 10. And then all I'm doing to convert the fractional part is just doing exactly what I said before, right? Where I'm dividing it by 2. See, this is just my generation part. Wait, this is basically what I was doing. But yeah, okay, so this isn't really useful. This is exactly what I was doing. There's maybe another way of doing it. Okay. Yeah, so this is the same thing, right? You're just generating one and continuing all the way. But it kind of sucks because you have to go all the way through it. And maybe there's another way of doing that's quicker, but maybe I'm just thinking of it wrong. Anyway, doesn't really matter. All you're basically doing is, I guess you can also do that. This way is like slightly quicker if you have like a really large initial number, because obviously if the way I was showing about before, right, you're going to divide it by 2 every time until you reach a point that is between 0 and 1. Like that's what I was saying, or between -1 and 0. It doesn't really matter. Again, the sign value doesn't matter. And with this way, all they're doing is they're basically just shortcutting that by looking at the value immediately, and if you convert it immediately to whatever you want, right, immediately to binary, right, then you can just read it immediately off, and it's there. So, for example, saying like 12, they can just immediately read the 12 as binary, and then they've got to do this normalization step, right? And the normalization step is basically just due to the fact that this number is quite large, and all you're going to effectively do is in this case, as you can see up here, right? Normalized number, we're moving the binary point, so there's 1 bit from the left. That's it. So you're basically just moving it across. So in this case, with 10, we're just placing the binary bit immediately afterwards. There's nothing to do. With a case like this, right? Again, with our 12, we can just place the 0.0 like this, and then all we're going to do is just read and move this right and figuring out how much we're moving it right by. And that's what's going to give us the exponent, right? The amount that we move it right by is basically how much we have to divide by 2 before we get to just between 0 and 1, right? That's effectively all this is doing. This is saying, okay, if I want to get between 0 and 1, or again, because it's subtract 1 from this, then how many times do I have to multiply by? Okay. Again, you don't really have to do this in an exam. Like if this was in person, I'd care more about it because you'd have to like sit down and do it in person. But like it's not going to be in person. It's not really that important. Yeah. Anyway, let's end this here. And we'll move on to the lab. Unless there's any questions or whatever. Or whatever. Lab. And the lab this week is pretty straightforward. So it's basically entirely based on floats, right? But it's more based on the float stuff that we did up here than the opposite way around, right? Which is why I talked about this. There should be. We can have a look in the outline quickly and see, but this should be a week test. Weeks 3 to 10. Typically, they release Thursday. Okay, so the lab, again, this bit is here is basically what we were talking about before. It's like the very first part of the tube where we talked about like the way they're partitioned. Again, you're going to have to use bitwise operators to extract things from it. If you notice here that you have a Uint32, right? So it's not a float anymore. It's already an unsigned number. So you can use bitwise arithmetic on it to extract. This one here, and while I do this, I'll set up the rooms. Try something a bit different with the rooms this week. We're gonna have a quiet room as usual. And we'll have fewer of the rooms for people to move between because I just think it will make it easier for people. So this one here is multiplying a float by 2048. The key thing about 2048 is think about, it says here you can only use bit operations in addition. So you can't just like times it by 2048, right, straight up. You have to choose arithmetic. And so maybe try to think about what the number 2048 is. And it says here, some of the functions from the previous exercise may be useful, and it tells you a hint. Adding 11 to the exponent is the same as multiplying by 2048. But the question is why? Well, the answer is 2048 is just this, 2 to the power of 11. So effectively, when we want to multiply something by 2048, we can just do this. So if our number, right, our binary float, whatever you want to call it, is going to be represented as this, as talked about in lectures, right? It's going to be 2 to the power of whatever your exponent is, minus 127, times by 1 plus your mantissa. So what will happen here, no worries, is that when we multiply these two values, right, the 11 will get added to this. Because as I said before, right, with exponential math, right, is that you can just add the exponent together if the bases are the same. So effectively, this just becomes plus 11. However, that's not always true, right? Because if we have, for example, a number that's infinity, we want it to remain at infinity, as we can see here. So you have to handle those edge cases. And the edge cases are listed here. So if it's going to be, if you're going to multiply it such that the exponent's going to be larger than, 200, or then what? 127, as we said before, because as we know, an exponent number, the largest value is this, minus 127, which gives us 128. Again, 128 is specialized specifically for infinity, so the largest possible value would be 127. So if we try to multiply this by 2048, whatever, 127, times by whatever, then this was going to be too large. So therefore, this becomes infinity, or more specifically, it becomes this, right? Or 8 bits. And again, here it's showing about the stuff here. Comparing floats. This is what I talked about before about the why we do biasing rather than doing the other thing, right? If we do biasing, we get really nice comparisons because the ranges go from 0, or rather negative 127, which is really negative 126, as I mentioned before, to 0, and then from 0 to 127, 128, which again is really 127. Yeah, floating point numbers aren't nice because there's a lot of these weird things where it's like, well, it can be this number, but it's actually really this number. But almost every question will tell you, or all the questions here will tell you that you just have to deal with normal numbers. So here, you can presume they're always normal, right? So you don't worry about the negative 126 or whatever. Oh, I can give a brief instruction on make if you want. Anyway, I'll talk about it in a second. But the last thing here we have here is printing float using any chart inputs. So this is a really hard one. If you want to go crazy, go for it. Oh, it's don't. And even comparing floats, this one used to be a normal exercise. It's now challenged because there's no partners, right? So we've split up. Now, if you want a brief introduction to what make is, let me just quickly do that. So the whole point of a make file, right, is you basically want to go, okay, I want to run a bunch of commands like GCC, typically, right? You can do make files with any language, but GCC and C is typically the standard one, right? And what I want to do is I want a bunch of commands, and I want a few things from this. The first thing is I only want to run them if the files have changed, right? If they haven't changed, don't recompile my files. Just only recompile the ones that need it. Second, I want it so that I get dependency management. What I mean by that is if I have a file that depends on another file, I want it so that when I change one file, the other files will always update, right? So that way, I kind of get a nice thing so that I don't have to go through and recompile my code because I changed a header, right? So headers always cause updates. The other thing, right, that I want from my make file is I want the ability to run these commands very easily without having to basically run GCC every time, right? Like manually. Because if I have like 20 files, it gets very complicated and annoying. And so I think it was shoot one where I had a make file, right? So if you watch the recursion video, I had a make file for that. And this is a very complicated make file just because I just use this make file almost everywhere. It's just an easy make file. But if you want a less complicated make file, I'll write one now, right? That's very simple. So the first thing about make file is we need to tell it what compiler we're going to use. We can use GCC here. Let me just tell it's a make file so we get syntax highlighting. We can also tell it's DCC. We can say I think there's another one called like 3cc or something, which is like the 25211. But it doesn't really matter. You can use Clang, you can use whatever you want. And then we're going to give it C flags. Now, C flags basically represents the flags or the options to our GCC argument, right? So, for example, an optimization level of 3. Another example would be -E, right, for producing macro, like for expanding all your macros. Like anything that you normally put there, you can put here, like -W or you can give it whatever, right? So in this case, I'm just going to keep it empty. Then the next thing we're going to do is we're basically going to there's a few ways you can write this, but what you'll typically see is you'll typically see like a phony clean at the bottom, which I'm just going to copy because this is just like a special thing that almost you always see clean copied, even the ones that you get given for labs. And all this is going to do is just remove all the files required, right? So it's just going to, for example, remove fib.o. It's going to remove maybe my final test.o, which is like what I run or execute, which we typically would just call test. We don't include the .o for the final file for some reason. It's just like, instead of calling it object file, sometimes we call it .out, right? Like a.out, for example. It's just like a standard, I guess, right? Making it easy. And so on, right? So you can include this for every single file. And this basically just denotes, hey, I want to clean up files. And so if we want to create, for example, our typical one, right, we'll have like an or somewhere, right? And I don't think I've got or here. I do not. And so if we want to do or, we can just basically say what or is equal to. So for example, when we say something like make or, we can say it's basically just going to compile Fibonacci, it's going to compile my test program, it's going to compile recursion, for example. I don't know what these things are. So for Fibonacci, what we do is we then define things that we require from Fibonacci. So the first thing we require from Fibonacci is the .c file, right? Obviously, we want to be able to compile that. The second thing we may require is we may require like a util file, which contains a bunch of utilities. Maybe you also require another one. Let's say it's called database, right? I don't know, we have some weird Fibonacci function. And then what we do inside this is we basically construct our command. We tell it what compiler we're going to use. We give it the C flags, and then we construct just as we normally would. Give it all the .o files or anything else you want to give it, and then you give -o fib. That's it. So we're basically running GCC with the flags, with all these arguments, compiling to an output. And then when we do, let's say, test, we can do the same thing. We can do like test.o, utils.o, in a database. And furthermore, you can also put header files here, and you probably should. So for example, I can put like fib.h, or I can put test.h. All my files are under include, as you can see here, just for like cleaning sake, but whatever. You can put includes as test.h, doesn't even matter, right? And these H files just basically tell her, hey, when these files change, I also want you to recompile this. And so, for example, when we say make or, it's going to compile fib, test, and recursion. Recursion doesn't exist, so I guess we can move it, right? It doesn't even matter. And C flags, and there's other stuff here. It's required, and right? Again, we don't give header files in here for the same reason you don't do it when you run it manually. Basically, it's just a way for you to write all your commands in here. As you can see exactly how you'd write it, though there's a bit of abstraction with these arguments. And then above it, we just put what the command's called and what dependencies the command has. And then at the very top, we just list all of them like this. You can go more complicated if you want and see this, and this basically defines a lot more variables. So this defines like the include directory, the compiler and the flags. It defines the output directory and the library directory. It defines the object. This is like the executable directory where like we put all the test runnables and stuff. And then it defines extra libraries to include. And then as you can see here, it defines all the dependencies. And then what this does is this is basically just going to grab all the dependencies one by one and just compile them effectively, because when it gets down here, this is where it goes through and compiles all the dependencies, as you can see here, right? So you do not need to use makefiles for the labs. And so this is going to go through and compile each one. And then the object file here is the exact same thing, compiles each of the object ones. And that's all it's doing here. And then you can ignore this stuff here. This stuff here is basically like kind of like special characters to signify what one you're talking about, because we're compiling multiple files. We're talking about specific ones. Again, you can ignore most of this. I think keeping it simple would be fine. And again, the way you run this is just make or example, right? In this case, there's no or because there's no or here, but I could give it an or, give it an or. Say my or is O directory or E directory. There you go, make or. That should be fine. Maybe it's just meant to be test. I don't remember. That doesn't even matter. I can just say make test or just make. Oh, there's no. Oh, that's why I'm not in the right directory. I was like, what? 2, 1. Yeah, there we go. So I should just be able to do what I did before. Do e/directory/test and make or, and nothing to be done for or because it's already compiled. If I clean it, then I recompile. You can see it will go back and recompile. And furthermore, you can see that when it was recompiling it, it compiled the .o files and then it compiled my final file. Okay, hopefully that makes sense and looks okay. And that's just a basic rundown of them. There's not too much more about them. Make files are pretty straightforward, thankfully. But they do get a little bit more complicated when you do stuff like this. So you can ignore this, just keep them simple for now. Or just not use them. So all you have to do for the assignment is, all you have to do for the labs is just say make or, and that will compile everything for you. Or you can just say like, I believe you can also do make and then followed by the name of the exercise, like make float bits, and it'll just compile float bits. Okay, so I've started the break rooms. I'm gonna stop recording so I don't forget.